Hello chemists, this is Miss Placino and you are watching Screencast 4.6 on polarity. In today's lesson we're going to talk about determining the polarity of both bonds and molecules. This is usually a pretty challenging thing for students to figure out, especially when we're talking about molecular polarity. Let's take a look at the do now. Which periodic trend can be used to evaluate how electrons are shared between two atoms in a bond? Explain your answer. As usual, pause the video, see if you can figure this out. Okay, if we're talking about how electrons are being shared between atoms in a bond, hopefully that's pointing you right at the electronegativity trend. I'm just going to abbreviate it EN. The definition of electronegativity is how tightly an atom is going to pull electrons towards itself in a chemical bond. So, direct definition. This is going to lead to bonds being what we call either polar or nonpolar, depending upon how they're shared. So it's a really important concept in chemistry. If we look at the electronegativity of two atoms, you can probably conclude that if they're relatively similar, they're pretty close together, those electrons are being shared fairly evenly. Whereas if you have a huge discrepancy between the electronegativities of the two atoms, we're going to see unequal sharing. So we'll start off with bond polarity, as it's the easier of the two concepts to understand. You can think about bond polarity as being a game of tug of war. Of course, atoms are not adorable puppies fighting over a cloth. They are atoms fighting over a pair of electrons. So we can use the difference in electronegativity between these two atoms to figure out how the electrons are being shared. If the electrons are being shared relatively evenly, we say that the bond is nonpolar. We're going to use the cutoff of 0.3 as a difference in electronegativity to kind of differentiate between nonpolar and polar. The closer you are to a difference of 0 in electronegativity, the more evenly or equally those electrons are going to be shared. So for example, take the diatomic molecule hydrogen. Hydrogen has a electronegativity of 2.2, so 2.2 minus itself gives us 0. That means that this pair of electrons being shared between the two hydrogen atoms is shared 100% equally. It's like a 50-50 split. Nonpolar means that the electrons are being shared unevenly. One atom is kind of hogging the electrons and pulling them closer towards itself, and the other atom is kind of left without that electron density. Usually the cutoff for polar, when we're talking about covalently bonded molecules, is between 0.4 and 1.7 when you subtract their electronegativities. Different textbooks might tell you slightly different numbers. I'd like to use these as our benchmark. Something like hydrogen chloride. Chlorine has an electronegativity of 3.2, hydrogen's is 2.2, so if you do the subtraction, you end up with a difference in electronegativity of 1. That means that when hydrogen and chlorine are sharing electrons, chlorine is kind of hogging them, and usually we represent that like this, where you've got the more positively charged hydrogen because electrons are being pulled away from it, and the chlorine is the one doing the pulling, so we draw the arrow in that direction. Here's another way to visualize it. This is showing us like an electron density, or the electron density cloud. We've got our hydrogen nuclei, we've got hydrogen atoms, we've got them bonded together, and you can see that it's kind of the same color everywhere in this diagram. That's representing even or equal sharing of electrons. On the other hand, the HCl bond is polar. We've got a very different picture here. We have hydrogen again, and we've got our chlorine atom over here. And you can see that there is a bigger, puffier cloud around the chlorine than the hydrogen. And the color has changed, where we've got this yellowish red color that's showing us a high electron density. And on the side where the hydrogen is, where the electron density has been pulled away, we see kind of these like greens and blues. It's kind of getting a little darker. As a result, we can put different signs on either side of the HCl bond. This little lowercase delta means slightly. So we would say that the hydrogen is slightly positive, again, because electrons have been pulled away from it. And on the other side, we've got the chlorine as slightly negative. It's more electronegative, so it's going to take that shared pair of electrons in here, and it's going to pull it towards itself, so we don't see equal sharing. Let's go ahead and do a little bit of practice. So use table S of your reference table to predict the difference in electronegativity and the polarity of the bond formed. So we'll start off with carbon and hydrogen. Small difference in electronegativity. It's just over the threshold at 0.4. This is a polar bond, but it's ever so slightly polar. It's not like it's a really drastic, big difference in electronegativity. Between oxygen and fluorine, we have a oxygen and hydrogen, we have a 1.2 difference in electronegativity. This is a polar bond. Oxygen is going to pull electrons towards itself. Fluorine and oxygen, we've got about a 0.6 difference in electronegativity. This is also polar. Fluorine's going to pull electrons towards itself. Between nitrogen and sulfur, it's the 0.4 difference between electronegativities, so polar again. For phosphorus and hydrogen, you end up with no difference in electronegativity. It's nonpolar. And for chlorine, a small difference at 0.2, making it nonpolar. So assessing the polarity of a bond is really just all about using table table S rather, and looking at the differences in electronegativity. Remember, 0.3 is the cutoff. 0.3 and below is nonpolar. 0.4 and above is polar. Molecule polarity is a little bit more involved. Instead of asking our electrons being shared equally between two atoms, we're looking at the distribution of electrons throughout an entire molecule. So something like methane, CH4, and again we've got this kind of electron cloud diagram as well. We can see that it's all the same color. That's suggesting that electron density is pretty even throughout the entire molecule. If you look at something like water's got its two unshared pairs of electrons. Water is a polar molecule. Oxygen has a very high electronegativity, and it's going to pull the electrons away from both of those hydrogen atoms, leaving us with a negatively charged oxygen side of the molecule and a positively charged hydrogen side of the molecule. And the key to predicting molecular polarity is all about drawing the correct Lewis structure. If you could draw the Lewis structure correctly, you're going to be in pretty good shape. So let's talk a little bit more about this. The first thing you want to do after you've got your Lewis structure is ask yourself a handful of questions. You can kind of follow along with this flowchart, and this should help you predict polarity. So does the central atom have unshared electron pairs? If the answer is yes, you're almost guaranteed that the molecule is polar. If the answer is no, you have a little bit more work to do. You need to take a look at the atoms that are bonded to the central atom and see if they're all the same. If all of the atoms bonded to the central atom are the same, that means that you have a nonpolar molecule. So no unshared pairs of electrons, the same central atom everywhere. Molecule has to be the same atoms bonded to the central atom, the molecule has to be nonpolar. On the other hand, if you don't have all the same type of atoms bonded to the central atom, you got more work to do. You need to look for polar bonds. So this is where you're going to look at differences in electronegativity between the central atom and all the other atoms that are attached to it, and see if any of those bonds are polar. If a polar bond is present, your molecule must be polar, and if none of those bonds are polar, then you're looking at a nonpolar molecule. So this sounds like a whole lot of hoops to jump through and assessments that you have to make. So let's do a little bit of practice with it. Determine the polarity of each molecule below. Well, first thing you want to do is draw the correct Lewis structure. So pause the video and draw them now. All right, let's check these out. So we have SiH4. Oh, I've got SiBr4 drawn here, my mistake. Regardless, it's a very similar Lewis structure. Silicon at the center, and then either bromine or hydrogen around the outside. BH3 should look like this. CH3Cl is going to look like this. And NH3 should look like that. So check your work, and again on that first one, sorry, I've got kind of a little bit of confusion between what I wrote and what I drew. Up next, we want to predict the polarity of the molecule. So assuming we've got all of these drawn correctly, that's going to make life a whole lot easier. So we can follow the flow chart. SiH4. Do we have any unshared pair of electrons on the central atom? Well, no, definitely not. So we want to look at what's attached to the central atom. It's all the same atom. So if they are all the same, that's going to be a nonpolar molecule. You can use a very similar line of rationale for BH3. Boron has no unshared pairs of electrons, and all of the atoms bonded to it are the same. Therefore, this is a nonpolar molecule as well. Let's take a look at CH3Cl. No unshared pairs of electrons on the central atom, so we've got to do a little bit more investigating. Are all the atoms bonded to the central atom the same? Well, no, they're not. Okay, so we've got yet another question. Are any of these bonds polar? If you look, yeah, all of these bonds are going to be polar. But the bond between carbon and chlorine is highly polar. You've got, like, I think a difference in electronegativity of 0.4 between the hydrogen and the chlorine, and it's bigger than that for carbon and chlorine. So the chlorine-containing side of the molecule is going to be a little bit negative. It'll leave the hydrogen side to be a little bit positive. Remember, this is a tetrahedral geometry. It's not flat like this. And we'll see a polar molecule for CH3Cl. Finally, we've got NH3. If you look, we've got an unshared pair of electrons on the nitrogen, so that's going to make it polar right off the bat. You can imagine that if this was drawn incorrectly, if you forget your unshared pair of electrons, we talked about it in lesson 4.4, molecular geometry, you're going to predict the geometry incorrectly. And then furthermore, you're going to predict polarity incorrectly because you have no lone pairs of electrons. You've got all the same atom bonded to the central atom, so you would predict that to be a nonpolar molecule. I cannot stress this enough. Be very, very careful when drawing your Lewis structures. Just continuing on with polar molecules a little bit more. Something like water we know is polar. So if we're trying to figure out which side of the molecule is pulling the electron density towards itself, in other words, which side of the molecule is going to have a slight negative charge, that's where you need to look at differences in electronegativity and really start to think about what's going on with how the electrons are being shared. So we can compare the electronegativity values. The atom that has the higher electronegativity is going to end up with that delta minus sign, and that's just going to tell us that side of the atom is a little bit negative. And in this case, with water, we know that oxygen is more electronegative than hydrogen, so it'll get the negative sign. The lower electronegativity side of the molecule is going to get the delta positive. So both the hydrogen atoms are going to have a slightly positive charge. Oops, I'm ahead of myself. This is why... this is how we explain the behavior of water. And we'll talk more about this later in the semester. But because we've got polar molecules for water, because water is a polar molecule, water molecules are going to be attracted to one another. You can imagine a neighboring water molecule. The slightly positive hydrogen is going to be attracted to the slightly negative oxygen in neighboring molecules, and that's going to kind of cause the water molecules to act like little magnets and stick together, and that's going to have some interesting effects on the overall properties of water. My suggestion is to go through, look back at all the practice problems where you've drawn Lewis structures, you've predicted geometries, get in there and start looking at the bond and molecule polarity. Bond polarity, again, it's just simply comparing the differences in electronegativity between the two atoms that are bonded together. Molecule polarity, you can use that flowchart to help you figure things out. Just like with the chart in molecular geometry, when you're practicing, try to wean yourself off using that flowchart directly. You know you're not going to have that when you go to take your test. So you want to kind of start committing some of that to memory. All right, that's all I've got for today. Thanks for watching, and I hope you found this helpful.